Okay, here's an example from class 22. I'm doing this specifically because I wanted to have some kind of power problem, and there wasn't any problems that dealt with power. So I have sort of the ridiculous situation where we have King Kong, and we have some kind of engine, and it's got like a 5-meter radius pulley in both places, and they're trying to lift King Kong up. The height, which is like 625 feet, which is just kind of dumb. But anyway, that's about half the total height of the Empire State Building. And at this position, the engine produces 1,000 kilowatts at 114.6 RPM, which seems like a very specific RPM. And the pulley and the drum are both 1,000 kilograms and 5-meter radius, which is huge. King Kong, we want to find the King Kong's speed at the new position, and if the engine operates at constant torque, okay? So it's the engine is going to have the same torque all the way through as it's moving here. It doesn't mean it's going to have the same speed, right? Because it's going to be like, I believe it's going to be increasing speed. So we want to find the engine power at the end. Right, so here you go. Here's our, what we do is we find out what the mass moment inertia of the drum is. I believe it's going to be the same as the pulley, right? The pulley, they said they were the same mass and the same radius. And then we find that RPM, we know what the RPM now of this drum is going to be. And we say that the power is, let's see, yeah, okay, no, we find the moment, because we could divide the power because it's a constant torque. So the moment and the torque are the same thing. But we're dividing that 1,000 kilowatts into by the 12 radians per second. And what that's going to give us is 83,330 Newton meters. And okay, so what we want to try to do is find out how many rotations of the engine is that going to take. So we know that it's moving 190. Where the hell did 190 come from? Yeah, 190 meters. Okay, so that's how far he's moving up. Okay, and divide that 190 by the radius, and that's going to give us the delta theta that this engine is going to turn. And we could say the velocity of King Kong in the first position with that at that RPM, right, that the thing is turning. You notice that I made it 114.6, and it turned out to be 12 radians per second. So I obviously went backwards and started out with 12 radians per second and got to that speed of RPM. We know that he's going 60 meters per second, which is stupid fast, 134 miles per hour. This is a very silly, silly problem. And, I use the old style. So this is the way that Johnston uses. Kinetic energy is T, potential energy is V. They do have work as being U. Sometimes they use W. So we say the energy before plus what's external stuff is equal to the energy after. So the kinetic energy at the beginning is going to be the disk right here, right, of the thing times omega 1, and then the pulley, it has the same angular velocity too, right, because the rope is going around it, so its tangential velocity is the same as the one down here, therefore it has the same omega. And then we also have the translational kinetic energy of King Kong, and we end up with 9.901 e to the 7 Newton meters. It's a lot of kinetic energy. Potential energy is 0 here at the bottom because we call that the datum. Sure, it starts and then it's just going to gain potential energy. So we have the added energy, right? External work energy is going to be the torque times the delta theta, right? So we calculated those up above. So we see that we're adding 3.17 e to the 6 Newton meters. We're adding that to the system. We find the kinetic energy at the end, right? So we don't know it, but we do have all of these terms, and we can put them all in terms of omega, So we know what the omega 2 is going to be. We had another choice. We could probably turn everything into like maybe velocity of King Kong or something like that. But omega seemed to be a good middle ground to use. And then the potential energy when we're done, he's been lifted up this high right here. So it's 1e to the 8. And so what we're left with is all of this stuff. And hopefully it's not going to go negative, because it seems to me that it totally could have, right? Because it was, yeah, we were close though. We were starting to get kind of close for it to go negative. We certainly wouldn't want that to happen. What it would mean is that he's probably going the other direction, right? But we'd still be taking the square root of a negative number, which would not be good. No. So the velocity of King Kong is therefore going to be that omega 2 times r. So it has slowed down. Yes, it has definitely slowed down from its original speed right there. Because it was a constant torque, it kind of had to, right? But there you go. There's King Kong's speed. And now we can figure out what the power is going to be. And we take that torque times that RPM, and so we see that it is still putting out quite a bit of power, 185 kilowatts, but not nearly as much as it was as 1,000 kilowatts to start with. And it was all because we decided it was constant torque, so it's 186 kilowatts. It was a silly problem, not quite sure if it's... I don't know. I wanted to have something where we combine this work energy along with the power, right? We want to make sure that we're thinking of power. Power is the time rate change of work. In this case, we've decided to keep that relationship going by making the torque constant. And now, how would that happen? Well, you'd probably have to have some kind of control system onto the thing that would like insist that the speed was allowed to vary. So the speed would be controlled by making the torque constant somehow. Like you might have some torsionometer on it or something along those lines. But anyway, it's a silly problem. Silly problem.